So that's the title. Main application of the following method is for trigonometry, but the idea doesn't rely on trigonometry. So that's what I want to introduce here. So here is the substitution rule. It's non-standard way of calling this one. The usual substitution rule call I'm going to call substitution rule 1. All right. This looks like this. If you're staring at this, what is this? Definite integral. Not definite, indefinite integral, antiderivative problem, right? And you realize that if your GU, well, the key thing is that if you're looking at this expression and you think about a U equals something, right? That's how the substitution works. The motivation of what U is choosing is highly depending on what you see in there, right? Hey, look at that part, its derivative out there. Is U is quite motivated. And here, not many of us really question deeply about, in that case, why is that U is there? After you experience a little bit, hey, there's a couple of things to try. So that's what that U is. And then we looked at this du dx, reciprocal, right? And if this altogether, it's inside, when you multiply reciprocal the derivative, it becomes just one function in terms of u, then we can rewrite this whole integral in terms of u integral, right? And then after you've finished integrating with respect to u, you plug it back in, what that u was in terms of x. That was the description, right? So, but substitution rule 2, which is what this session's about, or this section is about, actually look at this integral problem again, and kind of different order of operation. So you suppose you could integrate this when you integrated it, and you look at it up there, and you switch to u, and then evaluate the u. And you're looking at this integral, and think about, what if I look at this integral, and substitute it like x equals x of t, something completely different, out of nowhere. Now we're looking at this as a function, right? Antiderivative of little f of x. That's what that is, right? And plug in an x equals t, whatever you want. Then this whole thing becomes some function of t, as we just arbitrarily chose this xt there, right? Does that make sense? Integrate first and substitute later, but not passing through any of the u, just like that. Now this whole thing is function of t, and your question is that, can we actually find some function in here such that if you just integrate it with respect to t, then you get this result? Okay? So the question is again, here's a function f of x. If you integrate that first, and then plug in x equals xt, whatever the formula in there, the whole thing is a function of t. Now can that realize, can we actually do the antiderivative here directly to the t in terms of t? Okay? So the answer in here is that f of x, what that function is in terms of dt, that's this answer in here, is that x is replaced with xt. So you see all the x's in there, you replace that with xt. But what we are multiplying this time is dx dt, and not reciprocal. Now because of that, it began to be a little bit confusing. But if you write dt here, it kind of makes perfect sense. Kind of dt kind of cancels and becomes f of x dx. It looks just like before, f of x dx. Okay? So before that one, if you write it with this Leibniz's notation, that if you switch that to du, then you got to put that du down there and dx up there, so that it du's kind of cancel out, right? So that was the earlier substitution rule. That's why I call that one reciprocal of du dx. But I proved it in a different way, but the notation is very good, so that it kind of reflects naturally what's going on. But this one is that dt is going underneath in here, and then we have to write it dx dt. In order, it's somewhat different. They're quite similar in that way if you compare it with these two. But the key thing is that is this idea. So let's look at some example, weird example, so that you understand the procedure of this one. I think the example I have here is x dx. And if you look at this problem, there is no need to mess up with this one, right? Why would you mess? This is just perfectly fine. It's just an example to illustrate. So you think about integrating this one, and later, after that, we play with it. What if I plug in on x equal e to the t? All right? Then after you integrate with respect to x and plug in e to the t, and that's a function in terms of t. But what this substitution rule is saying is that this one can be just directly integral of something with respect to t. And this rule says this x is replaced by e to the t, right? And multiplied by dx dt. So what is dx dt here? E to the t. And that is not reciprocal. It's just dx dt goes there. That's the main difference between the first rule and the second rule. Second rule, you just put that derivative in there, no reciprocal. I think it's because of the order of operation. So e to the t goes in there. Is that right? Make sense? So this whole thing is better known as e to the 2t dt. Correct? So who knows how to integrate that e to the 2t? Quick way. This is e to the kt form, so it's 1 over k e to the 2t plus c. Remember that part? So if you integrate that one and plug in e to the t later, the substitution rule 2 is guaranteeing that this is going to be the result. 1/2 times e to the 2t. Right? So that's what it's asserting, but let's go ahead and verify that. We can actually integrate this one, right? What is the integral of that? 1/2 x squared, right? Correct? And you plug in x equals 2 and e to the t there. Let's calculate 1/2. E to the t raised to the second power. Then you see 1/2 times e to the 2t plus c. So we see, hey, that was correct. That's what substitution rule is asserting. You go through slightly different integral, but guarantee that, and you're going to end up with the same thing. Make sense? All right, examples. It's very important. Definite integral makes a big difference. So if you think about the order of operation, and you do understand why the substitution rule is slightly different. So let's look at definite integral situation. We want to calculate definite integral AB f of x dx, right? See if this method is going to do anything. Of course, that you want to calculate this one in terms of t, and you want to figure out if this one is somewhat related. Let me put the question mark over there. Is this true that I come up with some values of c and d, and it goes there in fxt and dx dt and dt out there. Without a, b, c, d, I wrote it as a rule that this is true, right? If you plug in x equals xt and later on. But if I have a number a and b in there, and can there be a c and d there? These two things are equal to each other. So when we are doing the u substitution looked like this. U equals ux, right? And x is being x equals a and x equals b, right? So you just calculate it, plug it in here, and you calculate it. If you actually go through the proof of substitution part 1, number 1, there's no problem. So let's look at it here. And substitution is kind of backward. X is xt. And these are the x values, right? X is going from a to b. So you're setting it as x equals a in there. And xt being b. And you think about, that c and d must be the number that correspond here. So some number t equals c that matches a, and t equals d that matches b, right? So that must be those number. But when you're calculating t is kind of backward here, you just have to plug into the formula, right? We have a formula with z equal to a. It seems like you have to solve that equation. There's no guarantee that there's no unique t's available. Can you imagine? There's two t values going down to the same a values if it is not one-to-one, right? Therefore, this part becomes a little bit weird. Which one are we choosing? And of course, if it is guaranteed to be unique, and there is no question, we'll just replace that unique value that goes there, right? So what condition again guarantees this unique value of C and D that matches this one? Is a one-to-one property of that substitution xt. So when you're doing this one with substitution rule part 2, we're requiring one more condition on that. What is that condition? Is one-to-one for the values considered. Is y equals x squared one-to-one function? X squared doesn't pass the horizontal line test. It's not one-to-one functions. But if you're just looking at between 1 and 5, then it's one-to-one. The graph passes horizontal line test. Overall, it's not. But just for the part that we are playing with, we're considering the integral, if that's just one-to-one, just over that value, then it's good. So what I'm saying here is that when you do definite integral, your substitution for this second rule, and be a little bit careful, you have to understand is a one-to-one function. Okay? And it kind of makes sense that here, when you try to pick C and you have natural question, what is the C and D? There are multiple choices in there. So you can't just put x inverse in there. All right, so that's one subtlety I'd like to mention about this substitution. And when we hit the example, I hope it's get clearer.